Okay, so here's what we were talking about last time. We were talking about the non-diagonalizable case, well, so systems, of this sort where the matrix is not diagonalizable. So just as a reminder of, the approach that we took, we decided to try the same thing that worked so well with the diagonalizable case, namely, let's conjugate, right? Attempt to diagonalize, right? Our failed diagonalization is a Jordanization, and by the usual method, you end up with a at least slightly simplified system, right? This is not a decoupled system, but if you look at the resulting differential equation down here, what you find is at least one of the equations is decoupled. So you solve for that one. That allows you to know everything you need to know to solve the previous one. And having solved that, you know everything you need to know to solve the previous to that. And, keep going till you're done. So, this will get you there. Now, it's a tedious process. This back-solving business took us an entire page of pretty tersely written algebra, right? I mean, I did not include every little bit on here, so it could have been worse than this. So this is quite a bit of inconvenience to do that way, but nevertheless does get you there. Once you solve, then for these z's, don't forget that what we were actually interested in is y. We were trying to solve this y equation, and you solve that y equation by multiplying by p, which we do here at the end. Okay. All right. I talked a little bit about, one of the shortcomings of this method is that it presumes that you do at least have a Jordanization. Right? That you know how to take a matrix and not only find the Jordan form, but furthermore, that you know how to find the Jordan basis, a Jordan basis, I should say. And of course, in general, we don't know how to do that. Right. So that's bad news. Quick reminder, one thing I did talk about last time, and I included in the email that I sent out Tuesday, I guess it was, is that even though finding the Jordan basis, from scratch is not something that we know how to do in this course, being able to identify in, for example, a situation like this, being able to identify the Jordan basis, that is something I expect you to be able to do. So in this case, for example, you should be able to identify that these, the columns of this matrix are the Jordan basis. Okay. All right. Make sure to be careful. Don't just assume that it's always the one on the left, right? Instead of writing A as a conjugate of J, what if I give you J as a conjugate of A, or any number of different little variations or twists that I could put on it, right? So don't memorize your way through it. Think about what basis is being used there, what basis is being used there, and then fill in the blanks of what this matrix has to be, what this matrix has to be, and then once you know, what are the input and output bases for those matrices, then you know which one's got to be the right one. Okay. All right, which we've talked about previously. Okay. Quick comment. Another way that you can find a Jordan basis is you can plug it into a computer algebra system. Right? So that, in practice, pretty handy sometimes. So don't forget that that's a possibility. Here's how you do it in MATLAB. I don't know how to do it in other systems, but I'm sure it's, comparable. Okay. Alrighty. Now, moving along. So I want to show you another case. Sometimes you get lucky and things work out really nicely. So let's consider the 2x2 case. And it turns out something really nice happens if you're looking at a non-diagonalizable 2x2 thing. And that is, non-diagonalizable 2x2, there is only one possible Jordan form. And that's it. I mean, there's just so many Jordan forms, right? This is the only non-diagonalizable Jordan form. So that's kind of nice. So in some sense, we really only have one problem to solve here if it's a 2x2 matrix. And a nice thing happens. Now don't forget this basis here, the V basis that we're using. This first vector is an eigenvector. That we know, and we know how to find eigenvectors. So we have found half of our Jordan basis. Okay. This other vector, okay, yeah, that's the problem. That's the vector we don't know how to find. Okay, so here's the next sort of wonderfully convenient thing, and that is that even though we can't find that second vector, what we can do is just plug in any random vector, doesn't even matter what, form a basis by taking our eigenvector and then just whatever. Any vector at all. I couldn't care less. As long as it makes a basis, of course. I mean, obviously don't pick a multiple of V1. Don't pick the 0 vector, something silly like that. Okay, any old vector. And what's wonderful is if you take this new basis then, and if you write your matrix with respect to that new basis, here's what it turns into. It turns into this. Well, I'll take a quick look at some of the details that yield this in a moment. But you get a matrix that is not Jordan form. Okay, so we have not Jordanized, and the nice thing about that Jordan form is, well, you can go through and you can back solve like we saw in the previous example. Well, here's the thing. Even though this isn't Jordan form, it's still back solvable. It's still upper triangular by virtue of the fact that this one number right here is 0. Right? So that's pretty convenient. So nice tool to keep in mind. You don't have to find the Jordan basis if it's 2 by 2. Just use the eigenvector and any other vector. Okay. So I want to say a couple of quick words about why this seemingly too good to be true thing actually works. Let's talk about this equation right here. A V1 is lambda V1. I claim that you can view that as that is what this column tells you, because in the language of that basis, right, what we have is the coefficients are lambda and 0. A V1 is, let's see, lambda V1, whoops, wrong color, plus 0 V2. Right, that's what that equation says. Of course, that 0 V2, I don't have to leave it there. It's 0. I can throw that away, which, of course, is the way I had it in the first place. Okay, but for kind of the same reasons, that's also what, I keep doing the wrong thing. That is also what I infer from looking at this column, going with respect to that basis. Right? With respect to the script W basis there, this first column, lambda and 0, means that the image of the first vector, still V1, is, well, lambda times the first basis vector plus 0 times the second basis vector. So I get lambda V1 plus 0 W. Which again, I can throw away. It's still 0, right? So this one equation, depending on how you choose to look at it, you can look at this one equation as telling us that lambda and 0 in the first column of the first matrix gives us also lambda and 0 in the first column of the second matrix. So the back solvability, being as it is a consequence of this 1, 0 right here, that back solvability immediately follows just by having chosen to reuse V1. Okay, so let me show you an example where you can how you can put this into practice. Let's look at this question here. There's a non-diagonalizable 2 by 2. By the way, there is a homework question that is 2 by 2, non-diagonalizable, just like this. So in order to answer that homework question, I think this is a great way to do it. I encourage you to consider this method. So there's our matrix, and step 1, you can find the eigenvector. Y'all know how to find eigenvectors. There it is. Okay. All right. Having chosen that eigenvector, for your second vector, pick any other vector. It doesn't even matter. I'm kind of arbitrarily picking that. No reason. You can pick anything you want. And having picked that arbitrary second vector, let's follow it through. This as our change of basis matrix. Those are the columns of that matrix. Again, be careful, right? Think about which matrix is a conjugate of which matrix. Think about which bases are being used where, right? The one on the right this time is our, what you might want to call P matrix. Okay. You put that there. Your original matrix A. There. And go through and play the game. And notice that even though we did not Jordanize, we did put this into a form that's back solvable. All right, we got that 0 right here. So our new system of equations, z prime equals kz, is going to be back solvable. And again, we've done an example with back solving. We did it last time. There's a lot of details, time consuming, but not that bad. Especially in a 2x2 case, it's not terribly bad. Okay, how are we doing? Any questions? Yes?
So W can be anything that's not parallel to one line?
Well, the second vector, yes. The W vector can be any other vector.
So
yeah.
Like 2, 2,
Don't choose 2, 2 because then you don't have a basis. And so for one thing, this matrix wouldn't be invertible, right? And so you can't, it's not something, the whole thing crashes and burns. But yeah, any other vector is fine. By the way, somebody asked me in office hours yesterday, not yesterday, obviously, Monday, I guess it was, why wouldn't I just use 1, 0 here? And you totally can. 1, 0 would be just fine. In fact, arguably 1, 0 would be better here as our W vector because it's got an extra 0 in it. Zeros always make arithmetic easier. So go ahead, right? I think that's a great choice. 0, 1. Yeah, sure. That would also be fine. Shoot yourself. Anything you want. I think the reason that when I wrote these notes, I think the reason that I did not choose 1, 0 is because if you do, in this case, as it turns out, this ends up being a 1 and inadvertently you've Jordanized. And I didn't want to leave students with the false impression that pick any second vector you want and you'll always Jordanize it. That is not true, right? So I picked one to be more representative of what you can realistically expect the benefits to be. Anybody else? Okay. All righty. Okay, so I'm going to make a definition here. It's going to take us a little bit of time to build up the tools that we need to make use of this next method. I'm going to show you. It takes us 4 or 5 pages. Sorry, but this has got to be done. And in fact, what I'm going to show you is a streamlined version already. There's a bunch of little details that I'm going to leave out. But the punchline is going to be a very nice method for solving differential equations, believe it or not. And it's going to come by defining something random and weird. Seems almost inappropriate, but I'm going to define what it should mean, or what I'm going to choose it to mean, to raise e to the power of a matrix. Doesn't that seem really kind of wrong? Yeah. I mean, after all, think back to elementary school. Raising a real number to a power means kind of that you're supposed to take that number and multiply it by itself that many times, right? So what does it mean to raise, to multiply e times itself a matrix number of times? That doesn't mean anything, right? It's completely unrelatable. All right. But let me point out, this is not our first time to do something inappropriate with the exponential function. Right? To plug something in the exponential function that you're really not supposed, it doesn't really make sense to, that doesn't, can you really do that? Namely, we've done it previously with imaginary numbers, right? So I asked the same question. If you have a real number, what does it mean to multiply it by itself I times? Seemingly kind of a garbage concept, right? So how did we define e to the power of an imaginary number? Well, we said, look, we're going to plug into the Taylor series. Same thing I'm going to do here. With imaginary numbers, and equally well with matrices, if you want to exponentiate it, all you really have to be able to do is to whatever that thing is, you have to be able to multiply it by itself so many times. Right? You have to be able to multiply by real scalars, and you have to be able to add the results. Anything you can do that with, you can exponentiate, in effect. Yeah? What do you think? Everybody on board with that? Seems a little weird, right? Okay. All right. So let me remind you, when we did that, we wrote down e to the power of imaginary numbers, so imaginary exponentials. Subsequently, we wrote down a bunch of algebraic properties. What does this definition satisfy? It's one thing to write down a definition, and for that to not immediately be garbage. That's nice, right? But you need to know what can you do that. How can you algebraically manipulate that if you want to have tools to be able to actually accomplish something? So we're going to do the same thing here. I have to write down some algebraic properties of matrix exponentials. The first one I'm going to do is let's ask, if you make this construction right here, e to the power of xa. Now before I go on, let's think through what this thing is. What is e to the power of xa? A is a constant matrix. So x times a is a matrix that is a function of x. Being as it is a matrix, I can exponentiate it by this definition. Being then as the result is a function of x, I can talk about taking a derivative with respect to x. So let's ask, what is the derivative with respect to x of this odd little creature here? And it turns out to not be so bad. This, of course, I can just write down by definition, is that taking a derivative of both sides. Let's look at this one term at a time. What happens when you take the derivative of the identity matrix? It's constant. Its derivative is 0. What's the derivative of x times this constant matrix A? Let's think that through here real quick. X times a constant matrix A, for example, right? Well, is XA, XB, XC, XD. If you're going to take a derivative of x times a constant matrix, you're just going to take a derivative term by term in that new matrix that has an extra factor of x in each term, and taking the derivative with respect to x, you just get that same matrix back. So I think that's a pretty plausible assertion right there. All right. Along those same lines, notice what we have in this next term. We have a constant matrix, right? It's got a different formula. It's a squared over 2 factorial, but it's a constant matrix that is being multiplied by x squared. When you take the derivative of x squared, you get 2x. And the 1, 2 cancels the other 2. So this differentiation goes down to that. Likewise for the remaining terms. What do you think? Everybody on board? Okay. So you get down to this. What does that do for you? Well, a clever move. If you just factor out the shared factor of A in each one of these terms, note that what is left over is exactly from that definition, e to the xa. The extra factor of A, of course, stays along for the ride, and we're done with the calculation here. Altogether, e to the xa has this as its derivative. And it's wonderful when stuff works out sort of unexpectedly nice. Let me explain what is nice about this. If this were a Calc 1 class, and you have e to the power of x times a constant, well, it would have been a scalar constant in a Calc 1 class. E to the power of x times a constant, you take the derivative, you just go whip out an extra factor of that constant. And what we're seeing here is that with this seemingly out of the blue definition of matrix exponentials, even when the constant factor is a matrix, it remains that matrix factor just pops out. Okay, so it's really good news, really. Okay. All right, and it's actually really, really, really good news. As follows, using that fact, we can immediately write down all solutions to this initial value problem. In other words, every initial value problem I could ever want associated to any homogeneous constant coefficient, chapter 6 style differential equation, any initial condition, here is the solution. That'll do it. And we just have to directly confirm. We have all the tools we need now to confirm that this does solve the differential equation and it solves our initial condition. And let me walk you through those steps. To plug this into the differential equation, I just have to observe that differentiation, we already agreed, kicks out an extra factor of that matrix A. So right off the bat, the algebra that we just showed tells us that this solves the differential equation. Okay. Next question, how do I know that this satisfies the initial condition? Well, we've got to be a little bit careful here. I need to take this x equals 0. I need to plug that into there and see what my function becomes. First observation, if you plug in x equals 0, this exponent becomes the 0 matrix. And notice that the 0 matrix, when you exponentiate it, just think about this formula here. Right? If M is the 0 matrix, that formula turns into e to the power of the 0 matrix is the identity matrix. So all the other terms just disappear. And if e to the 0 is the identity matrix, then notice that when x equals 0, the value of this becomes just y naught as required. So, we're done. It would be tempting at this point, in fact, even to say, hey, we're done completely with all homogeneous first-order constant coefficient systems, because there's the answers. Not only do I have all the solutions, I know how I can break them down by initial values. You give me any initial value problem, there's the answer. Done. Doesn't that seem a little too good to be true? Okay. All right. There's only one disappointment with this. There's only one. Let me get out of sales pitch mode and into realism. Here's what's disappointing about this. Even though this is the solution, I don't know how to evaluate this function very effectively. Right? I have a definition for matrix exponentials. Yeah, I've got an infinite series up there, and I can write down an infinite series of matrices, I suppose. And yes, that is, technically that's the right answer. But if it's not something I can evaluate, what good is it to me? Right? We don't know how to evaluate matrix exponentials effectively. So that's really all that the rest of today's talk is going to be about, is how do you evaluate matrix exponentials? Specifically, if I want to multiply a matrix exponential times a vector, which I really want to do because it satisfies our equation. If I want to multiply a matrix exponential times a vector, how do you do that? Okay, all right. So first, let me observe that it's actually a little bit easier than that. I don't technically need to multiply matrix exponential times every vector. All I really need is to multiply by a basis worth of vectors. Not infinitely many, all possible vectors. If I can figure out how to multiply our matrix exponential times just a basis of vectors, then nice punchline, these functions will be a fundamental set of solutions, and of course, this being a linear algebra class, a fundamental set is really kind of a better way to understand the solutions that we're looking for, right? We know that these functions form a vector space. Let's understand them taking advantage of the fact that it's a vector space. Let's understand it by way of a fundamental set. Okay. So our problem has now become, it's not how do I multiply matrix exponentials times arbitrary vectors, it's how do I multiply the matrix exponential times I get to choose whatever basis I want, whatever it would be the easiest in vectors to multiply by the matrix exponential. That's all I really need to be able to do. Okay. How are we doing on that so far before I go on? Okay. Now I am going to ask you all to prove this theorem. It's not that big of a deal to prove. We know we're looking for an n-dimensional vector space. We know this is in vectors. So really all you need to do is prove that this list is independent. How are you going to prove that that list is independent? Well, you're going to compute the Wronskian. In fact, let me just go ahead and give it away for you. You don't even have to compute the whole Wronskian. Just plug in x equals 0 and compute the Wronskian. Which I claim is actually not that bad to do. In fact, it's pretty straightforward to compute this Wronskian when x is equal to 0. It's going to use some ideas that we've already talked about. So you have to piece those little details together. But so this is the exercise I'm leaving you with. Compute the Wronskian of this list, matrix exponential times basis. Compute that Wronskian when x equals 0. Confirm that it's non-zero. And then, of course, that gives you what you're looking for, that this list is independent. Okay, so details for y'all. As usual, if you have questions, feel free to come to office hours. Ask in discussion section, whatever. Okay, so what basis are we going to pick? What would be the easiest vectors that we can think of to multiply by the matrix exponential? And I am going to skip a bunch of the algebra here. There is a bunch of tedium algebra. Not that big of a deal, and anyone who's curious is welcome to come to my office hours. I will flesh it all out in gory detail for you. But here's a nice punchline to some inconvenient algebra. These kinds of expressions. Matrix exponential times a vector. Here is an alternative formula for computing. And it ends up being the case that this is a great convenience. Let me tell you why it's not clear if this is helpful. For one thing, the formula on the left looks much more compact than the formula on the right. Right? Which one of these looks prettier? Clearly this one. So why would I want to deal with this? A matrix exponential here, this is an infinite series. Well, yeah, but so is here I have an infinite series of matrices too. So why do I care? What's the benefit? The benefit is that this matrix is a special matrix. We know some vectors, some special vectors that have a wonderful relationship with A minus lambda I. Right? And so instead of having an infinite series involving the A matrix, it's going to end up being pretty sweet to have an infinite series involving the A minus lambda I matrix, because I can choose some special vectors. Probably guess what they are. Special vectors that have, again, this wonderful relationship with A minus lambda I. Okay. So, in fact, let's think about eigenvectors. If I want to multiply a matrix exponential times an eigenvector, well, A minus lambda I. What do I get when I multiply A minus lambda I times an eigenvector? 0. Right? This is a reference back to Chapter 5. In Chapter 5, one point of view that we had on eigenvectors where eigenvectors are in the null space of A minus lambda I. Said differently, A minus lambda I times eigenvector is 0. So that term, because V is an eigenvector, that term kind of goes away. Here, maybe I better scratch. That term goes away in a puff of smoke. Okay, now what about A minus lambda I squared? What does that do to an eigenvector? Well, the first factor of A minus lambda I that you multiply gives you 0. And other things that you multiply after don't matter because they're being multiplied by 0. Right? So all these terms go away in a puff of smoke. All of the infinitely many terms in the infinite series go away, and all you're left with is matrix exponential times eigenvector is, well, e to the lambda x times the identity matrix. It doesn't do anything. Times eigenvector. So you get that. And so we've evaluated this expression, matrix exponential times specially chosen vector, eigenvector, easily computable formula, right? Scalar exponentials, no problem. This is good old familiar stuff multiplied by the eigenvector. So nice result because of that result there. How are we doing? Everybody on board? Okay. So to whatever extent I choose eigenvectors in my basis, here let me zoom out. To whatever extent I choose eigenvectors in that basis, I get stuff that's easy to compute for these matrix exponentials. So again, keep in mind we get to pick any basis we want, any basis at all. The moral of this story is pick all the eigenvectors for sure. I mean, no doubt. Definitely pick eigenvectors as most you possibly can. If you have an entire basis consisting exclusively of eigenvectors, definitely do it. Take them all, right? And of course, you might even recognize that. Look at this. You get the exact same solutions that we derived, I guess it was Friday, in the diagonalizable case. Exponentials times eigenvectors. So this reproduces a bunch of previously known results. Okay. What remains is, what if you don't have an entire basis? What if you can't fill out a basis with eigenvectors? What do you do with the other vectors? And you might guess reasonably that, well, not enough eigenvectors means not diagonalizable. What have we in the past done in the non-diagonalizable case? We've resigned ourselves to accepting that, well, at least we can Jordanize. In other words, we've used a Jordan basis. And it's going to turn out that here, if we use a Jordan basis, that will be as good as we can do. And it's not bad. Okay. Now, first thing I want to do, let me not get ahead of myself. Don't forget what we're doing with the vectors that we choose. Whatever vectors that we choose, that we then need to multiply by a matrix exponential, those vectors we're going to plug into this formula. So we're looking to understand how is it that this formula can help us understand, how does this formula dovetail with Jordan basis vectors. This formula is chock full of a minus lambda I. So if I want to be able to use this formula, my next thing I need to figure out is what does a minus lambda I do to Jordan basis vectors? And to this point, we haven't really written that down in that form. We don't really know the answer to that question immediately. So I just need to address that question. What does a minus lambda I do to a Jordan basis vector? It's not that big of a deal. It's just some details. Let me remind you what our Jordan form looks like. Here's our Jordan form. Right, don't forget, if you have a Jordan form, then inside of it are a bunch of individual Jordan blocks. We're going to focus our attention on a single Jordan block. Remember, blocks correspond to columns. Columns correspond to basis vectors. Okay, so this one Jordan block is telling us a bunch of information about these specific Jordan basis vectors. So let's focus our attention on them. Again, we're going to take this one Jordan block at a time. Okay. And I want to look now individually at these equations, at these columns, and see what these columns tell us. Let's start with this first column. Remember, columns give you the images of the basis vectors. So that column tells me this. Notice that column that I've highlighted. This is the what you might call the first column that hits that block. that basis vector is W1. We already knew from previous discussion that that was an eigenvector. And writing down that equation, we see it again, that W1 is an eigenvector. Okay. All right. Well, here's what I'm going to do now. Just rewrite that with respect to the standard basis. You get this. Move one term over to the other side, and out comes one of the pieces of information I was interested in. I now know what A minus lambda I does to that Jordan basis vector. It's an eigenvector. Right? But still, it's one of our Jordan basis vectors, and A minus lambda I on that Jordan basis vector. Here's a convenient formula for it. Again, we already knew the answer was 0. But now we're just going to take that same process and apply it to these other columns. Let's look at these columns here. These other columns, those are going to tell us about these other Jordan basis vectors associated to that block. For those other Jordan basis vectors, those columns tell me that. The only difference being these columns are the ones that have the 1s in them above the diagonal. So that gives me that 1 right there. Therefore, this extra term. Okay. Again, kind of old news. But now let's just write that down with respect to the standard basis and move things around just as we did last time. This, with respect to the standard basis, I would write like that. Move this term over to the other side. Oops, I didn't make that long enough. Move that term over to the other side like we did before, and out comes that equation. And here's again what we needed. Our goal was to figure out what does A minus lambda I do to Jordan basis vectors. Here's our answer. Very crisp little answer. A minus lambda I does to a Jordan basis vector simply to return the previous Jordan basis vector. That's it. Just the previous Jordan basis vector. And you can see it in the algebra. Those 1s above the diagonal, give you this 1 in that algebra, which is what gives you this 1 there, which is what gives you that 1 right there. The reason you get the previous Jordan basis vector, you can trace it back, it's just because of the 1s above the diagonal directly. Okay. All right. Let me big picture overview again here. What are we doing? We're trying to understand matrix exponentials times vectors because they solve our initial value problems. They are solutions to differential equations. So what is a matrix exponential times a vector? Specifically, we're choosing a special basis of vectors so we can understand just those. We're using this formula here that tells us matrix exponential times special vector can be understood simply by looking at, get right down to it. What does A minus lambda I do to those vectors? Right? Now we have information on the next page that tells us exactly what A minus lambda I does to our Jordan basis vectors. It just sort of moves them one back in the list. And so now we just have to put it all together. Here's our little summary, by the way. These equations, there's the whole justification, but these equations here break down to the first Jordan basis vector, our eigenvector, goes to 0, and all of the others, A minus lambda I simply goes to the previous. A minus lambda I sends each vector in this list simply back to the previous vector in that list until you get to the eigenvector, at which point you go to 0. So, nice little shorthand for what's going on here. Okay, let's, again, put it all together. Here's what we're trying to understand. Trying to understand this equation. We're going to plug in Jordan basis vector. Here's what happens. Let's put this Jordan basis vector into there. This becomes Wi. the ith Jordan basis vector. This therefore becomes wi. That same ith Jordan basis vector, and here we go. We're just going to follow it through one term at a time. The identity times wi gives me wi. That's it. That's an easy one. Okay, wait a second. What does a minus lambda I do to wi? Oh, wait a minute. A minus lambda I takes whichever Jordan basis vector you're looking at, and it simply turns it into the previous Jordan basis vector. So a minus lambda I wi gives you wi minus 1. And of course this this factor of x here comes along for the ride. Everybody see what happened there? Okay. Okay, next. Okay, now here we have a minus lambda I squared. Okay, we got to be careful with this one. A minus lambda I squared. What does that do to wi? Let's go back to our list. A minus lambda I squared. We're going to take one of these vectors, one of these Jordan basis vectors. The first a minus lambda I gets us to the previous one. Then we're going to multiply by a minus lambda I again. That gets us to the one previous to that. Altogether, multiplying by a minus lambda I squared just moves you back 2 vectors in the list. It gets you to the vector 2 previous in that list. So, wi minus 2. Again, this coefficient out front stays along for the ride. Yeah? Everybody on board? Okay, et cetera, et cetera. So you just keep getting additional factors of a minus lambda I as you move along in this infinite series. Additional factors of a minus lambda I just sends you further back in the list of Jordan basis vectors. wi minus 1, wi minus 2, wi minus 3. It keeps going back further and further. You can see it in this list. It's sending you back each additional term, each additional factor keeps sending you back further in that list of Jordan basis vectors until you get to the eigenvector. And then the next term that has yet another factor of a minus lambda I, that sends you to 0. Right? Because that's what this yellow formula up there says. That means that for terms that have that many factors of a minus lambda I, however many factors of a minus lambda I it takes you to get to 0, you're at 0 multiplied by continued powers of a minus lambda I. Who cares? You're multiplying by 0. So the moral of that story then is this process continues. You keep getting more and more terms until you get to the eigenvector. Once you get to the eigenvector, you stop. And notice that's what we do in this equation. We get back to the eigenvector, and then we stop. So this original equation that we had up here is an infinite series, but after a certain number of terms, they disappear, right? They give you zeros. So this, as it applies to a Jordan basis vector, this is no longer an infinite series. This is a finite summation of terms where you just keep going backwards in the list of Jordan basis vectors until you get to your eigenvector. And then you're done. Okay. All right. Let's put this into practice then. Let's actually crank this out. Here's a question to deal with. Let's suppose we want to solve this differential equation. By the way, you'll recognize this is the exact same differential equation that we started today with. Right? And I bemoaned that it took what was it? I forgot, 2.5 pages of algebra, some of which I had been pretty terse about, so it might take you more than that. I mean, it's a pretty significant amount of work to go through that whole, Jordanize and back solve. That's a kind of a pain. So here's what we're going to do instead. You look at this same given algebra, and we again infer that here's our Jordan basis. Again, keep track of which basis is in which language and interpret appropriately. Make sure to don't pick the wrong side, don't pick the wrong matrix. It's easy to get that backwards. In this case, they're on the left. So there's our Jordan basis vectors. That's the basis we're going to pick. With that Jordan basis, all I have to do is multiply that Jordan basis times the matrix exponentials. I have to evaluate these three things, and there's my fundamental set of solutions. Practically speaking, then what it boils down to is how do I evaluate these matrix exponentials times Jordan basis vectors. Here's where we use our formula. You see our formula up there? All right, here it is. That's how you multiply matrix exponentials times Jordan basis vectors. With applying this to W1, keep in mind you stop when you get to the eigenvector. This being W1, that's a 1, which means that's a 1, which is the eigenvector, so we stop and the rest of this goes away, and this turns into just that. So there's our first solution in our fundamental set. Everybody okay? By the way, notice we could have shortcutted this because knowing that this is an eigenvector, several pages back we have an existing formula for matrix exponential times eigenvector. Is this. Okay, right. So now let's do it for the second one. How do I multiply matrix exponential times the second Jordan basis vector? Well, here I is 2. So that's a 2. That means that's a 2. That means that's a 1, which is our eigenvector, and so we stop. And the matrix exponential times the Jordan basis vector is that, which I write there. Same formula, it's just the implementation's a little bit different because, well, it's the second vector in the list, so I get 2 terms by the time I get back to the eigenvector instead of just the 1. Let's see the third one. Same formula, right? Again, matrix exponential times Jordan basis vector. Here, I is 3. Put a 3 there. So that's a 3. That's a 2. That means that's a 1, making that the eigenvector, and we stop. And matrix exponential times Jordan basis vector is that. How are we doing? Everybody on board? Just plugging into the... It's a weird formula, right? But we're, in fact, just plugging in to that formula. Okay. And, in fact, we are kind of done at this point. It's all over but the end zone celebration. Don't forget we know that our first Jordan basis vector, W1, is that. You can see it right there. Furthermore, that W1, when you multiply it by x, gives you that right there. And that W1, when you multiply it by 1/2 x squared, you can see it showing up right there. Right? Likewise, W2, you see it there? W2 multiplied by x, you see there. W3, you see there. And here is our fundamental set of solutions. And by the way, just in case you might not have noticed, that's the exact same fundamental set of solutions that we got after several pages of tedious back solving in our original approach to this problem. And here we got it simply by citing a formula. Right? So this matrix exponential business is crazy powerful for this specific application of solving, these kinds, constant coefficient, non-diagonalizable, homogeneous linear systems. Really, really powerful. Once you know the Jordan basis, you can pretty much just write down the solutions. Okay, so big fan. Let's see here. I am out of time. There's a little bit more I want to say about this that I'll comfortably be able to do on Friday, and then we're going to move on to non-homogeneous stuff on Friday. Okay, see y'all later. Have a good day.